Hello, today we're going to talk about two-sided search models. In this model there's going to be a worker who's looking for a job, but also an entrepreneur who is looking for a worker. Now, a job is going to be a match between one worker and one entrepreneur who together draw a value of productivity from some random distribution. When they look at that productivity that they've drawn together, they jointly decide whether or not they're going to accept it or reject it. In principle, you could think that they may disagree on whether or not to continue together, but the way this model is going to work is that there's going to be bargaining among the entrepreneur and the worker over the surplus from their joint match. And if there is no surplus, they will of course not agree to share it. There'll be nothing to share. And if there is some surplus, then they will share it by some rule. We're going to follow the Mortensen-Pissarides model, which is going to have a very simple way of sharing the surplus. We'll discuss later how there could be alternative ways of doing this. If we want to introduce a two-sided search model, we need both workers and employers. So let's start with workers who search for jobs. And again, before, a job was just a wage coming out of some distribution. Now a job is going to be something slightly different. Entrepreneurs are a completely different kind of agent who can create jobs. That's a cost C. And what they do is they create essentially a job opening, and to keep it open, you have to pay cost C. If you don't find the worker, that's too bad. You'll have to try again next period and pay cost C again. So maybe C is like an advertising posting cost. On the other hand, if you find the worker, then that's great, your job is filled, and off we go. Now, when they get together, a job is a match between a worker and an entrepreneur. And together they produce Y, where Y is drawn from some distribution which has the PDF of little f as before, and with CDF of big F. Next, as before, the unemployed gets a benefit B, and jobs are destroyed exogenously with probability lambda. And here is how jobs and workers find each other. If there are U workers looking for work and V open jobs, so we're going to refer to an open job as a vacancy, then the number of new matches between workers and jobs is a function m of U and V, where M is homogeneous of degree 1. For example, M could be Cobb-Douglas, although that's just one example. Finally, one more thing is that when this worker and this entrepreneur meet, it's going to be unclear how exactly they're going to share the output Y that they produce together. So we're going to pursue the approach in Mortensen and Pissarides, which is to assume that there is a bargaining parameter beta that governs how the surplus generated by the worker and the entrepreneur is divided. We'll look at that in detail later on, but to cut a long story short, what we're going to do is impose the cooperative Nash bargaining solution. And if you haven't come across that before, that's okay. We'll get to it soon enough. Next, some notation. First, as before, we're assuming that worker utility, instantaneous utility that is linear, as before. Second, let Q be the probability that a firm with an open vacancy, an active job opening, finds a worker. Then it's going to be that Q is going to be a function of the number of matches. Specifically, of course, if everyone is treated the same, then it's going to be the number of matches divided by the number of vacancies. And now, remembering that the matching function is homogeneous of degree 1, that means that this is the same as just the regular matching function with both its arguments divided by V, which simplifies to this. It's only a fraction of U over V, not of U or of V itself. Here's a bit more notation. Let theta equal V over U. This theta is also known as labor market tightness. Then we have that Q is just some function of labor market tightness, theta. Moreover, if we assume that M is increasing in both its arguments, that makes sense. If there are more workers or more vacancies, there should be more jobs created. Then we should have that this Q is increasing in U over V, which means that Q is decreasing in theta, since theta is the reciprocal of U over V. So in other words, we have that Q prime is strictly negative. That'll be useful later. What else? Well, the probability that a worker finds a job, rather than giving it a name, observe that that is going to be something similar to this. It will be the total number of matches divided by U, the number of unemployed people, which again is going to equal the following: multiply top and bottom by V, and of course this divided by V is just this. So this is all the same as Q of theta, and this V over U is theta. So the probability of a worker finding a job is also a function of theta, but it's this function, theta Q theta. So we'll need to keep all of this in mind as we go forward. Next, we want to write out the value functions of all the agents involved in this environment. First, let's start with an entrepreneur who has a filled vacancy. In other words, they are working with a worker. And let's call their value function J. Let's also use what we did before when we were talking about the one-sided search model, where we're first of all going to measure value functions at the end of the period. In other words, if this is what happens in one period T, and T plus 1 starts here, and the arrow of time continues off in this direction, then rather than measuring the value here, where just before consumption takes place, which is where we did when we were talking about the growth model, instead we're going to measure it here, after everything has already taken place, and we know that tomorrow the agent is going to start discounting, whether with beta or with 1 over 1 plus R, whatever happens tomorrow. In addition, as you remember, we can just start writing down the value function in flow form. So the flow for an entrepreneur who has a filled vacancy, if we're going to call their value function J, then the flow from being in this state is RJ. Now, RJ, of course, depends on Y, the draw that they got from the distribution F whenever the worker and the entrepreneur got together. That should equal Y minus whatever wage they have agreed on, which again results from them sharing the surplus according to some rule we'll get to later. Now W, of course, also depends on Y. And lastly, what possible change could there be in the state of this firm? Well, so far we've had Y fixed, just as before we had wages fixed. So Y doesn't change. What can change is that the entrepreneur could go from having this job to not having this job. So the additional thing that could happen is with probability lambda, they will lose J going forward because they're no longer having a job, and they will gain whatever happens to entrepreneurs when they don't have a worker. Let's just call that X for a second, where X is the value of being an entrepreneur without a worker. Now, in addition, we're going to assume that there are many entrepreneurs. If there are any opportunities to be snapped up from becoming an entrepreneur and posting a job, someone will come and fill it. In other words, what this does is that it makes x equals 0, sort of like a free entry condition. And if x is 0, then this just becomes the following. Nice and simple. Next, what about the unemployed? Let's make their value function u. Again, going straight into flow form, we have the r of u is going to be equal to b. That's what they get from being unemployed. But things could change. What could change? The unemployed worker might find a job. And that happens with probability what? With probability theta q theta. If they find a job, what happens? Well, they will get the maximum of taking the job or not taking the job. If they don't take a job, then they stay in the state of unemployment U. And of course, what that means is that the change in their state could equal 0 if they decide to stay there, or if they decide to take the offer, they will lose their status as an unemployed person, but they will gain whatever value there is from being employed with a firm, with an entrepreneur that's producing output Y. And let's call that W of Y. So that's what a worker gets when their firm has Y. Now, of course, there's a distribution of Y, so we have to integrate over that. And let's assume Y has some range, and dy completes this equation. Next, we have the people who are working. They are getting W of Y. And again, going straight into flow form, R of WY equals the wage that they are getting plus any change that could happen in their status. Well, the change that could happen is that they might lose their job, which happens with probability lambda, in which case they lose WY, but they gain U, the value being unemployed. More conditions. The next condition would be this free entry condition, which is that the value of creating a vacancy should equal whatever cost there is to creating a vacancy, so that there is on the margin no arbitrage to be had by creating one. So remember, the cost of creating a vacancy or of keeping a vacancy open for a period is C, and that has to equal, well, the expected value of a vacancy. With probability Q, that vacancy is filled, and if it is, well, two things could happen. Either the job is created, everyone agrees that there is some value to working together, and then you get the difference between J of Y, which is what you get if you're operating with a worker, minus the value of being here without a worker, which of course is 0. So it's the max of that, and what you get if the worker turns you down, or if you decide not to stay together with the worker, which of course is 0. as we'll see later, it turns out that the only time that you would turn down the worker, or that the worker would turn down you, is if the surplus that you have to share is 0. In other words, there'll be no situation where one of you wants to stay together and the other one doesn't. This, of course, we have to integrate over the possible values of y, and that is our condition. Finally, here is where we need to be a bit more careful. There is the bargaining equation, which tells us how the workers and the firms are going to bargain with each other. That condition is going to be the following. What's the surplus generated for a worker of being in the firm? Well, it's going to be what they get from being in the firm minus what they could have gotten without the firm. What is it that the firm gets? Well, same thing. They get the value of what they would get if they were together with the worker minus what they would have had otherwise, but that's just 0. The way I've written it, this has that this surplus must be equal for both of them. But more generally, what we're going to assume is that there is some parameter that governs how much of the surplus goes to the firm and how much goes to the worker. And let's call that parameter beta. 1 minus beta here. Beta is used because it has to do with bargaining. What happens here? If you set beta equals to 1, this is 0. And so that means that the firm gets nothing. If you set beta equal to 0, then this is 0, and that means that the worker gets nothing. Their value of getting this job is the same as if they were unemployed. And for different values of beta, you can get anything in between. Now, this particular bargaining rule, where you share the surplus according to a parameter, may seem like something convenient or something arbitrary, but the reason that it was appealing to Mortensen-Pissarides is because it has multiple microfoundations. First, it has a microfoundation in cooperative game theory. It turns out that this is the solution to the Nash bargaining problem, where beta has to do with the weights afforded in bargaining to the different agents. Second, it has a non-cooperative bargaining foundation as well, because it turns out that it's related to the solution to the Rubinstein-Wolinski alternating offers bargaining problem, where you have one agent making an offer, the next agent can accept it or reject it, in which case the next agent may get to make the next offer, and where beta relates to the probabilities of each agent making an offer. If you take the time interval between the agents making offers to 0, what you end up with is the same thing. And that's why at the time this was an appealing solution. However, there are many other ways of dealing with situations where there may be surpluses to be shared between agents. We're going to continue with this one, but just keep in mind that there are other possibilities such as wage posting, among others. And there are also environments with directed search, and that's why search theory remains a rich theory of investigation. So, how are we going to solve this? We're going to solve this by observing that most of these conditions here are in fact linear. There are several unknowns here. JY is unknown, U is unknown, WY is unknown, Q theta is unknown, and this wage is unknown. So we have 5 equations and 5 unknowns, except that, of course, some of these unknowns are functions rather than being numbers. At the same time, there's a lot of linearity here, and that's going to help us solve it. So let's start by doing the following. We're going to start by defining the difference between what a worker gets and what an unemployed worker gets. So we're going to define d of y equals w of y minus u. Now, from here, you can see very clearly that from the wage bargaining equation, this is d of y. So d of y is a simple function of what the firms get. Now, using this, we look at the equation for U. For big U, we see that, take that equation, we can just replace this with d of y. Great. And observe that the integral here can be rewritten like so. Where we can take this outside because, of course, that times that is what we had before, and that times this is just 0. Now, also use this in the entry condition, which is here. We can write that in the following way. And we can put that in to the equation for U to get something much simpler. This replaces this entire integral. Wow. And one of our functions has been eliminated from this equation altogether. And finally, notice this Q cancels with this one. So what we have here is pretty simple by comparison. Next, notice that J of y and big W of y can be rearranged. That's pretty straightforward. If you take J of y, you can easily show that this is just r plus lambda times J of y. And so J is just y minus the wage over r plus lambda. And similarly, if we go up here and get the expression for W, we can do something similar. We can bring this over here, factor out WY, divide both sides by r plus lambda, and we get this expression. Plug this into our bargaining equation, which is here. And what do we get? We get this equation that again is eliminating everything that's a function here except for the wage. And if you work through the algebra, you'll see that this is going to simplify quite a lot, because this u is the same thing as minus u times this, where of course this plus lambda u is going to cancel with this minus lambda u. Now we can multiply both sides by r plus lambda. That's gone. What next? Expand terms. Beta y minus beta the wage. 1 minus beta the wage times this. Notice that we can cancel minus beta from both sides. Minus beta times the wage from both sides. And we end up with the wage being simply this, which again is pretty simple. It depends only on y. We can then rewrite this on very simple terms, because remember up here we had a very simple expression for UR. We're going to call this the wage equation. All we need to know is theta, which is an aggregate variable, the labor market tightness. And with this equation, we will get the wage WY for any Y. Now, what is this doing? It's telling us that the worker is going to get some share of output beta, but in addition, they're also going to get 1 minus beta times something here that's got to do with the cost of creating a firm. In other words, the firm and the worker are sharing both the output that they can make together, plus the costs that the firm incurred to create the job, and also the benefits that the worker gave up in order to join the entrepreneur in this position. Finally, let's combine a couple more equations. So let's take the free entry condition here, combine it with J, which we have here. We'll get the following. Then we plug in the wage equation and we get this. Now, notice that this is 1 minus beta y, and everything here is 1 minus beta. So this is just 1 minus beta times y minus all this stuff. We can simplify, multiply both sides by r plus lambda. This comes out. Now we don't have a fraction anymore. And now multiply all these things inside by 1 minus beta. And we end up with this equation, which has an alternative writing. Now let's be careful about the limits of integration here. Before, this goes over some range of y, and let's just imagine without loss of generality that it's 0 to infinity. Of course, if f is 0 above some value, then of course we can have an upper bound here. Just like with the one-sided search model, we're going to do a transformation here. Remember that as before, this maximand is a strictly increasing function of y, our variable of integration. We're taking the maximum of that expression and 0, and since this is strictly increasing in y, what this tells us is that there will be a reservation level y star above which the job is created because there's some surplus to be shared, below which no job is created because there is no surplus to be shared. And so we can just write this in a simpler fashion as y star of this expression. And so the equilibrium of this economy is characterized by two equations. One is this one, and the other one is, of course, the definition of y star. And what is that? Well, it's just simply that this whole expression must equal 0 for y equals y star. Alternatively, put all this over here, change the sign, divide both sides by 1 minus beta, and here you have exactly the expression for y star. Now, as before, we can use graphical intuition to show that an equilibrium, if it exists here, is unique. How so? Well, once again, we can do so by drawing graphically in this relevant space. Before, it was the space of the reservation wage W star, but now it's the space of the reservation output Y star. And what's the other value that we still haven't pinned down? It's labor market tightness. The first equation, the one that defines a reservation wage, you'll recall, once again, is linear. That was the second equation, the definition of Y star. What about the other equation? Well, let's go back to our algebra. Now let's try and figure out the shape of this second equation. First, let's notice that we can simplify this as follows. We can split out this from the integral to get the following. Notice also that these are constants, and so we can take them out. How does that help? Well, let's set this equal to 0 now. So Y star is 0, and this is 0. This is what's going to tell us the value of theta that makes this equal when we assume that Y star is 0. It's the value on the y-axis, or on the theta axis to be precise. Now this, of course, is just 1. And so you can put this over here, the expression on the left is strictly increasing in theta. This is increasing in theta, this is decreasing in theta, but it's in the denominator. And this will be a positive number so long as the expected value of y is larger than b. You can see that by factoring out that. And we could simplify this. As so. This factors out, and we get that this is just 1, and this is the expected value of y. So as long as the expected value of y is greater than b, this is a positive number, which means that this is a positive number. And this goes from infinity, if theta is so much that q of theta is 0, down to some constant, which must be, well, if we set q of theta to be 1, then this is the constant. So as long as this holds in general, that this is greater than that, then we will have some theta so that this holds. So we do have some parameter restrictions here. But so let's just assume that, and so the positive intercept on the theta axis of this line here is positive. Now, more generally, at that value, this, since we're presumably below y star, is going to be negative. So as we raise y star from 0, we're erasing negative values from our integral. And that's great. It means that we are increasing the right-hand side. The left-hand side doesn't depend on y star. So if you're increasing this side, to make the entire expression hold, we'll need to be increasing this side, which of course means increasing theta. Now, presumably, if there is a y star, at some point, this will hold with 0 at that particular correct value. And if we continue increasing past that point, well, now the value of this expression is positive because we're above y star. This is strictly increasing in y star. And so if we keep on increasing y star past the correct value, we're removing positive values of this integrand. And so now this thing is decreasing. In order for this equation to hold, that means that theta must be decreasing above y star. What have we shown? We have shown that if there is any y star, then under certain conditions that we can guarantee that the wage equation line starts here, it's going up at first, but if it ever crosses y star, if it crosses the definition of y star rather, then it's going to be going down thereafter. And so again, there will be one and only one value that makes both of these lines cross, and that is going to be our solution to the model. Finally, 2 points. One is that so far, none of what we did assumed that the unemployment rate was a state variable. We mentioned it early on, but then it never showed up again. And one could ask whether perhaps, although we showed that in principle there could be equilibrium behavior that does not depend on the unemployment rate, alternatively, perhaps there could be equilibria that do depend on the unemployment rate. That was an open question. People were satisfied with the fact that you could show that there was an equilibrium that did not depend on the unemployment rate, as opposed to theta, the labor market tightness. But I got an email some years ago from Randy Wright, who said that he had such a proof. Unfortunately, I can't find it, and I don't see it in the published literature, but apparently it's possible. Second, there is the broader question of what are the unemployment dynamics in this environment. And it turns out that they're very simple. In the one-sided search model, you had unemployment dynamics that were related to the reservation wage. In this context, you're going to have the exact same dynamics as a function of the reservation productivity. The reservation level of productivity, above which matches will persist, below which matches will be cancelled. And so the exact same function for the transition across dates for unemployment, and the exact same expression for the unemployment rate in steady state will hold in this environment, just that we need to substitute the reservation productivity instead of the reservation wage. I hope this was useful, and we'll see you next time. Good work. See you soon.